Welcome to this third exercise of surface water hydrology in the part on the concepts. This third and final exercise in this part will be about routing. We will discuss both river routing and reservoir routing. As you remember from our theoretical lectures, these two parts of routing are actually the final part that we have discussed there, where we first had the precipitation in the first class, actually in the second. We had some infiltration, evapotranspiration as rainfall losses, where we had also an exercise on this topic. We had surface runoff, which was the topic of the previous exercise. And then finally, when we had this surface runoff, we needed to route this through a reservoir or through a river to finally get to our final outflow of the catchment. Now, we know if we apply flood routing that we want to know, for example, along the river, how the flood wave transports along this river or through this reservoir. And we describe this by looking at different characteristics, like the flow velocity, and the water level. Important to remember is that when we are applying hydrological methods, which we will do now within this exercise, we will only get the flow values at the outlet. And what we try to do is actually to get downstream characteristics based on a known situation upstream. During the theoretical lectures, we saw a possible application of such methods. If we had a reservoir more upstream, where we knew how much water, how much flow would flow into the reservoir, or next to the reservoir, for example, if the reservoir is next to the river and can be filled up, we want to know actually how much we should fill the reservoir to avoid a flooding in the downstream part where there could be a city, for example. And if we know how this flood wave that comes in, represented here by this hydrograph, if we know that one, how it transforms while propagating along the river, we can know if this is really necessary downstream to fill up this reservoir to avoid the flooding. We knew for the hydrological methods that they are quite simple and a lot faster than the hydraulic methods which we also discussed during the theoretical lectures, and that, for example, we can use them for real-time control or for long-term simulations. There are some limitations, however, in the application of these hydrological methods, like, for example, we cannot have a looped network, or we cannot apply it for situations where we have backwater effects. And like I mentioned just before already, from the hydrological methods, we will only receive the flow at the outlet, and this as a function of time. Now, to get flow velocity and water levels, we would require additional equations that would calculate the flow velocity and the water level based on, for example, the flow. What we in general do is that we start from our continuity equation, which we will know already. The change in storage is equal to what comes in minus to what comes out. But like in general for the hydrological system, we need an additional equation to solve this conservation of mass, the continuity equation. And this additional equation will be a storage relation. And this storage relation can be, for example, a function of the inflow, the first derivative of the inflow, the second derivative of the inflow, etc. Or also the outflow, and then also the derivatives of the outflow. Now, how this storage equation really looks depends on the characteristics of the system at hand. In some cases, you can have a very simple, unique relationship between storage and outflow, linear or nonlinear. But there is also a possibility to have a linear equation of the inflow and the outflow. Or there might be some derivatives involved of the outflow or possibly even of the inflow. So those are more typical equations for a storage equation, which will give you a relationship between the storage and inflow, outflow, or one of those two or the two together. And the relation will actually be important for the influence on the propagation of the flood wave. And in that way we can calculate then the outflow discharge or the inflow based on the inflow discharge and then the storage. What we knew for the river routing was that we had typically a situation where we had a hysteresis. And in that case, we knew that the maximum value of the outflow would be after the maximum value of the storage, which can also be seen here at the hysteresis, in the Q versus S graph. And what we also know, of course, based on our continuity equation, is that this maximum storage value is just at the location where our inflow is equal to the outflow. Here we can see clearly that this maximum outflow value will be after the maximum storage value. The situation is different for reservoirs, where we see that we have a unique relation, and we also have the fact that the storage will be maximum at the point where also the outflow is maximum. And this is also noticed when we look at the two hydrographs, the inflow and outflow hydrograph. Then we see that the maximum outflow value is just at the point where the inflow is equal at the outflow. Now, let's have a look at our assignment for today. The first part will be on river routing, and there it's asked to give or determine the parameters K and X of the Muskingum river routing based on the inflow and the outflow hydrographs that are given in this table. And when we have this K and X value, it is asked to determine the outflow hydrograph of the same river reach if another inflow hydrograph is given. So based on the K and the X values that are determined from our first question, we will determine the outflow for this new inflow in the second question. And then in the second part of this exercise, we will look at reservoir routing, and there we have a reservoir with a weir at the outlet, and the reservoir has a length of 10 kilometers, and the cross section is trapezoidal with this equation, where B is the large base, small b is, so capital B is the large base, small b is the small base, and then the change over the height is given with a factor alpha, which is equal to 1. At the weir crest level, so just at the small base, this small value b is equal to 190 meters. And then we also have the information that the water level can go up to a maximum of 2 meters above the weir crest. The outflow from the reservoir is given by this equation. This is a typical weir equation where Q is equal to 2/3 of CL, C being the discharge coefficient, L the width of the weir, and then the square root of 2g, where g is just the gravitational acceleration, and then h is the head of the weir over the weir crest, so the water level above the weir crest. C is in this case 0.6, L is in this case 20 meters. And it is asked to define and present graphically the storage outflow function. So we will try to determine the storage outflow function for this reservoir, And then, based on what is called the level pool routing method, we will calculate the outflow of the hydrograph from this reservoir. And there's a certain inflow given that comes into the reservoir, and it will be based on that inflow that we determine the outflow.